Good afternoon. Myself Raashid Firoz, and I am going to take a class of strength of materials, and the topic is biaxial stresses and Morse circuit. So today's topics are uniaxial load, two-D stress system, principal stresses, maximum shear stress, and related problems, and then Morse circuit and related problems. So we all know that when a uniaxial load which can be of the form of tensile load, compressive load, or shear load, applies. A uniaxial shear is formed within the material. So the shear stress can be found out by load by area. When this stress reaches a critical value, like yield stress or fracture stress, then the failure of the material occurs. So this is a very simplistic view, but suppose apart from this axial compressive stress, tensile stress also acts like this. Then, how can we find the stress which will determine that what will be the critical stress for which the material will fail or not? Also, for apart from this tensile stress, we also provide a shear stress here and also the surface below. Then how can we interpret that what will be the stress which should be considered uh, to find the critical value of the failure stress? So suppose we have a biaxial stress system here. Here sigma x acts in a x direction. This is x direction, and this is y direction. So sigma x acts on x direction, and this sigma y acts on y direction. Both are tensile stresses, and this tau xy is the shear stress, and to balance that stress, also a tau xy stress acts here. This all four tau xy stress are equal in magnitude. So for this type of system, how can we determine stress which we can consider as a critical stress for failure? So for that, we have used principal stress and maximum shear stress we determine for this type of system. So before determine that, we can determine the normal stress which acts. Suppose we consider a plane. This CP is a plane which is at an angle theta from this CB plane. So at this plane, normal stress acts sigma n, and shear stress acts tau. So this sigma n and tau can be determined as the formula for sigma n will be sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. And the shear stress will be sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. We can derive these two relations by equating. For that, we have to consider this portion PBC, and we have to consider this portion PBC, and we have to uh, e- this equate all the forces by caused by this stress sigma x tau x y, when we will equate the forces, then this type of relation can be found. But for preparation of exams like GATE, these derivations are not important. Rather than this formula and application of this formula to problems are essential. So, if we want to determine that, we are taking this plane CP at an angle theta. We can change this theta. We can take at 10 degree, 20 degree, 50 degree, 90 degree. So, we want to determine that at which plane what will be the maximum normal stress. Okay. So, for determining the maximum normal stress sigma n, we can write for maximum value of sigma n, delta sigma n divided delta theta will be 0. So slope of sigma n will be 0. This will give tan 2 theta p equal to 2 tau xy divided sigma x by sigma y. When we apply this formula, means first we take the derivative of this sigma n and we equate with it with 0, then we will get this relationship. So with this relationship we can find theta p, which provides us the angle at which the maximum normal stress will act. Similarly, for maximum tau, maximum shear stress, we take the derivative of this and equate with 0. That will give us cot 2 theta equal to minus tau xy divided sigma x minus sigma y. So with this theta, we can determine that at which angle from this BC plane, at which angle a plane contains the maximum shear stress. Remember this theta p is for maximum normal stress, which will be different from this theta, which is for maximum shear stress. So now we will see how to determine principal stresses. We have these two formula for normal stress and for shear stress, which is the function of the acting stresses and theta. So what is principal stress? Principal stresses are the normal stresses which act on the planes, and those planes are known as principal planes where shear stress is 0. So the planes where shear stress is 0, okay, that planes are called principal planes. And the at principal no shear stress acts, only normal stresses acts, and those normal stresses are called principal stresses. Okay, so when we put tau is equal to 0 at this relation, okay, so that will give us tan 2 theta p equal to 2 tau xy equal to sigma x minus sigma y. Okay, so we can see that position of principal is planes which is same as for maximum normalcy. In the previous slide, we found out that what will be the theta p for maximum normal stress. So if we compare this with that, both relations are same. So the conclusion is that principal planes and is same plane where the maximum normal stresses acts. Okay, so at principal plane maximum normal stress also acts and shear stress will be 0. So when we get this theta p, okay, we can find out the theta by inversing this tan inverse 2 tau xy divided sigma x minus sigma y, and we put that theta p to this sigma n. Okay, so that sigma n will give us two relations. Actually, we get sigma 1 is equal to sigma x plus sigma y divided by 2 plus minus root over sigma x minus sigma y divided by 2 whole square plus tau x y square. We will get plus minus because this will be a quadratic equation. And a quadratic equation, when we put the square root, we give both plus minus signs. So the equation with plus sign is called major principal stress, which is also maximum principal stress. Okay, and with minus sign is also principal stress, but this is called minor principal stress. Okay, and it will be lesser than the major principal stress. Okay, so principal stresses are the normal stresses which acts as the plane where shear stress is zero, and major principal stress is also the maximum normal stress which can act for the given applied stresses. Similarly, we can find maximum shear stress for the given stress system. So, for maximum shear stress, we the slope of the shear stress will be zero, and when we put this equation, means when we derivate this equation and put to zero, then we will get this relation which has been shown earlier also. Then from this equation theta can be found, and when we put this value of theta to shear stress, so because this theta corresponds to the plane where maximum shear stress acts, so when we put the value of theta for maximum shear stress, we will get maximum shear stress. So maximum shear stress will be tau max is equal to tau max is equal to sigma 1 minus sigma 2 divided by 2 equal to root over tau sigma x minus sigma y divided by 2 whole square plus tau x y square. So sigma 1 and sigma 2 are sigma 1 is major principal stress and sigma 2 is minor principal stress. Okay, so let's move further. Planes of maximum shear stress also have normal stresses, but principal planes have no shear stress. Okay, so at the planes where maximum shear stress acts, normal stresses also acts at that plane. But at the principal planes where principal stress acts, there will be no shear stress. This should be remembered. Now let us see some problems, whatever has been taught. Okay. So a shaft subjected to torsion experiences a pure shear stress tau on the surface. The maximum principal stress on the surface, which is at 45 due to the axis, will have a value. So we can see that here a pure shear stress acts. So there is no axial stress, no tensile or compressive stress. Only shear stress of the magnitude tau acts. Okay, and we have to determine the maximum principal stress at the surface, which is at 45 degree to the axis. So the theta here is 45 degree, and here four options are given, and this is a gate question. So for solution we have this formula. Okay, so here is sigma x and sigma y both will be 0 because here no sigma x axial stress active, and only tau xy. For tau xy we will put tau xy as tau. Okay, this will be tau, and this both will be 0. Okay, so after putting this, obviously we will get tau. So answer is tau, but here in the four options given we don't have any option as tau. So but if we Analyze this D option. It is 2 tau sine 45 degree cos 45 degree. One knows sine 45 degree is 1 by root 2. And similarly, cos 45 degree is also 1 by root 2. Okay. So this after multiplying this get half 1 by root 2 into 1 by root 2, and this half cancels. So the ultimate answer will be tau. Okay. So sometimes the gate questions are given that your final answer will not match exactly with the options, but if you break down the options, you can match that your answer with the equation. So this type of questions also comes in gate exam. There is one more formula from which we can find out, because their angle is also given 45 degree. So we know the general normal stress formula. This is only for principal stress, but this is the general formula where for any given theta we can find out what will be the normal stress for that plane. Here also, if you put all the values of, we will get tau sine 90 degree, because 2 theta will be 90. And if we break, we know sine, if we consider this sine 90 as sine 2 into 45, so sine 2 theta is equal to 2 sine theta cos theta. So ultimate answer will be 2 sine theta sine 45 degree cos 45 degree, which is the option D. Okay, there is one other problem here, given in a biaxial stress problem. The stresses in x and y directions are sigma x equal to 200 megapascal and sigma y equal to 100 megapascal. So the maximum principal stress in megapascal. So there here sigma x and sigma y given, and tau is 0. Okay, these four options are given. Again, we will, for maximum principal stress we know the formula, and we put sigma x is equal to 200 and sigma y is equal to 100 megapascal. Then we will get 200 megapascal. So this is the answer, which is option B. Um, this is assertion and reason type of question. So here is an assertion is given: if the state at a point is pure shear, then the principal planes through that point, making an angle of 45 degrees with plane of shear stress carries principal stresses whose magnitude is equal to that of shear stress. Okay, so we have done this problem. Uh, Here also it is the problem of pure shear, and the theta is 45 degrees. We have done this problem here, pure shear and 45 degrees. So the value of principal stress we get tau, which is equal to the value of pure shear stress applied. Okay, so the same thing is here. Here is given pure shear stress x and at angle 45 degree with the plane of shear stress. Carry the principal stresses whose magnitude is equal to that of shear stress. So principal stress and shear stress will be of the same magnitude. So this is true. We have seen in the previous problem. Okay, but the reason is given that complementary shear stresses are equal in magnitude, but opposite in direction. If we note this statement, that complementary shear stresses are equal in magnitude, that is also true. What is complementary shear stress? This stress, okay, this stress and this stress, these are called complementary shear stress. Oh, sorry, these two stresses are shear stress, and this is called complementary shear stress with respect to this one. Okay, suppose I give it 1 and 2, then 2 is complementary shear stress with respect to 1, and 1 is complementary shear stress with respect to 2. So these all shear stress are of same magnitude. Okay, so this statement is also true. But what are the options? Both A and R are individually true, and R is the correct explanation of A. So both are true, but if we consider reason R as the correct reason for A, so there is no logic here. R is saying that complementary stresses are equal, that is will be equal for all the problems. But for the particular problem given in A, this is not the correct reason. This is complementary shear stresses are equal in magnitude for all the cases, mm, for not for any particular case. Okay, so this is not the, if there will be some other, suppose instead of 45 degrees here is given 20 degrees. Okay, then the principle is, then this will be not true A, but R will always be true. Okay, so this is wrong. R is not the correct explanation of it. In B, we get both A and R are individually true, but R is not the correct explanation of it. So this is reason is true. This is true that A and R are individually true, but R is not the correct explanation of A. And these two are cannot be applied because R is not false and A is also not false. So only B, option B is correct. There is another problem. A tension member with a cross-sectional area of 30 millimeter square resists a load of 80 kilonewton. Calculate the normal and shear stresses on the plane of maximum shear stress. So here only one one axial load is given. Okay. So if and there is no shear stress, applied shear stress. So we consider, if the consider the load acting in x direction, then sigma x will be load by area, which is 80,000 divided 30. So sigma x will be 2666.67 megapascal, and sigma y is equal to tau xy is equal to 0. Okay. So we have to calculate the normal shear stress on the plane of maximum shear stress. So first of all, we have to determine what is the plane of maximum shear stress. For determining the plane of maximum shear stress, we can use this formula, and we can determine this theta. After putting all the values, we will get theta is equal to 45 degree. Then we will use this formula of normal stress, and we will put the value of sigma x, sigma y, and the value of theta. From this equation, we will get the value of normal stress, which acts as the plane of maximum shear stress. Okay, this is the plane of maximum shear stress. When we apply this theta to the normal stress, then we will get the normal stress at that theta. That means at the plane of maximum shear stress. Okay, which is has been asked here. Okay, and also we have to determine the maximum shear stress also. So for maximum shear stress, we know this formula, and after putting all the values, we will get this answer. So these two are the final answers. Now let's come to Morse circle. If we are given a biaxial stress system like this, we have seen it in earlier slides also. So this we have found the normal stresses, shear stress for a particular plane at theta angle uh, in the form of equation that is called analytical method. Okay. Also maximum shear stress, principal stresses. Okay. But how can we represent and find out these values using the graphical method? So Moore circle provides a method to visualize and find out the normal stresses, shear stresses, principal stresses, etc. By a graphical method. So for a given stress system, how can we construct a Moore circuit? Let's see that. First, we have to draw two axes. One is sigma axis, okay, one is tau axis. Sigma axis will be horizontal, tau axis will be vertical. Okay, now here first we have to plot 2 points. One is for sigma x, sigma y. Okay, so we can see that both sigma x and sigma y both are tensile stresses. Okay, in Moore circle diagram, tensile stresses are taken on the positive side. Okay, and compressive stresses on the negative side. Okay, so since both are tensiles, both are taken on the positive side. Okay, so there must be a unit of sigma x, maybe in megapascal or Newton per meter square, whatever. So suppose sigma x value is 50, 100 unit, just for example, and sigma y is 20 units. Units with any unit system, but that should be consistent for all the stresses. Okay, so we will plot 100 here, and we will plot 20 here. Okay. Similarly, if tau xy is suppose also 30. Okay, then we will from sigma y we will draw a vertical line upwards equal to 30 units, which is tau xy, and from sigma x we will draw a line vertically downwards equal to 30 units. Okay, then in the next step, what we will do, we will join these two points, which is T and S, and these 2 points will intersect the sigma axis at C. Okay, then we will consider this C as center, and this point T or S point. Okay, so this TC or CS we will consider as radius. Okay, so considering CS as radius, we will draw this circle. Okay, so Morse circle is complete, but we have how to represent the different stresses on Morse circle. So the circle, the point where the Morse circle intersect the sigma axis. Okay, we can see that this circle intersects the sigma axis at 2 points, sigma 1 point and sigma 2 point. So the greater value will is considered as sigma 1 point, and the smaller value is as sigma 2. Sigma 1 is major principal stress and sigma 2 is minor principal stress. And this value CT or CS is maximum shear stress. Okay, this is tau max. This is tau maximum. Okay, so we can get the value of sigma 1, sigma 2 and tau maximum. And suppose we want to find out the normal stress and shear stress. Okay, not the principal stress or maximum stress, just general normal stress and shear stress at an angle theta we want to find. So what we have to do from the center, we have to draw a line at 2 theta from the sigma axis, 2 theta, which will join the circle. Okay, so that join the circle at point P. So the normal stress sigma n will be this value, means from the center to, means this RP is the value of normal stress, and this value QP is the value of shear stress tau. Okay, so with this we can find out different stresses using Mohr circle. Okay, so here if we want to find out what is the distance between the center and the original center of the this two stress system axis O, so or what is the value of OC, so this center is at sigma x plus sigma y by 2, because we can see this is sigma x and this is sigma y, this is in between this value, so this is the average of sigma x plus sigma y by 2. And what will be the radius of this circle? R. So the radius of this circle can be found that if we consider this triangle CSL, this triangle CSL, so this value is, means CL is uh, sigma x minus sigma y by 2. Okay, this value is sigma x. CL is equal to sigma x minus sigma y by 2, and this value is tau xy square. Okay, that we know. So this is the diagonal, and we know the formula of diagonal is equal to root over. So the value of the radius will be root over sigma x minus sigma y divided to whole square plus tau xy square. So you should remember these two formulas. These questions are asked in yet another exam, that what is the radius of Mohr circle, or what will be the center of the Mohr circle. If we want to give the coordinate, so the coordinate of the center will be sigma x plus sigma y by 2 comma 0, means at a sigma axis the value will be sigma x plus sigma y by 2, and at tau axis it will be 0 because it is at the sigma axis. Now so we have said that this is sigma 1 and sigma 2 are principal stresses, but but we want to assure that it matches with the formula. So sigma 1 comma 2 is OC plus minus R. Suppose this sigma 1 point is OC plus this is the radius of the circle. This is the radius of the circle from C to sigma 1. Okay, and also if sigma 2 will be what? OC minus the radius of circle. Okay, this to sigma 2 is radius of the circle. So for sigma 1 it will be OC plus R, for sigma 2 it will be OC minus R. OC is, we have seen that OC is sigma x plus sigma y by 2 plus minus, and R is, we have seen that root over sigma x minus sigma y by 2 whole square plus tau x y square. Okay, so which is, or which is the formula we have got by analytical method also. And this R is also maximum shear stress, value of maximum shear stress. Okay, you can see the relation is same as maximum shear stress. Okay, this P gives the value of sigma n and tau at theta from principal plane. Here we give the value to theta, but actually it gives the value at theta from the principal plane. Okay, so let us see some problems. So here it is given which one of the following mode cycle represents the state of pure shear. So they here only shear stress is acting, no axial stress is acting. So sigma x and sigma y will be 0. So when sigma x and sigma y will be 0, then the center C will lie on O. Okay, because if you see that if this sigma y and sigma x 0 both will be 0, then this C will come here at O. Okay, and at O we can draw the tau upward and downward, and then we can draw a circle from O to this distance. Okay, so here is only this option gives that type of circle. Okay, this is the value of tau, means applied shear stress, and sigma s and sigma y is 0. Let's move to the next question. The Mohr cycle of plane stress for a point in a body is shown. Okay, this is the Mohr cycle. The design is to be done on the basis of the maximum shear stress theory for yielding. So we have to find out the maximum shear stress. Then yielding will just begin if the designer chooses a ductile material whose yield strength is. So we have to find out, first we have to find the maximum shear stress, and then we will find the yield strength. Okay. For that sigma x, and what will the, from this diagram, what will there is no shear stress. Okay, why then on the basis of maximum shear stress, then yielding will just begin. Okay, okay, wait, sorry, this is not, this will not be sigma x, but this will be sigma 1 and sigma 2. Okay, from this diagram we know that the where the circle acts to the sigma axis, that 2 points are major and major and minor principal stresses. So, and as the sign negative suggests that these are compressive stresses. Okay, so sigma 1, this means major principal stress is minus 100 or 100 megapascal compressive stress, and sigma 2, that is minimum principal stress, is equal to minus 10, that is 10 megapascal compressive stress. Okay, so tau max formula we have seen earlier, that sigma 1 minus sigma 2 divided 2. These two are major and minor principal stresses. Okay, and it will be equal to 45 megapascal. For a ductile material, we consider the yield strength is equal to 2 into maximum shear stress. Okay, so the yield strength will be minus 90, that means 90 megapascal compressive stress. So for today's this is it, and I hope you would like this class, and thank you.